Hello everyone, welcome back. In this video we are going to talk about flood frequency analysis. I'm calling it part 1 because there will be another video or two that will discuss flood frequency analysis. So let's get started. This is where we stopped in our last video. So we learned what exceedance probability is and what return period is. So building on that, in this video we will continue our discussion on flood frequency analysis. So this slide just describes what flood frequency analysis is, and briefly we have discussed this before. So basically in flood frequency analysis what we try to do is we try to relate a flow magnitude to a certain return period, and in some cases we try to find the flow magnitude or value corresponding to a certain return period. So the magnitude and return period or exceedance probability, they are all related. So for example, a flow that has a very high exceedance probability will occur more often compared to a flow that has less frequency or less exceedance probability. Okay, so higher the exceedance probability, lower the flow magnitude, and vice versa. But before we get into the flood frequency analysis, let's talk about the data that we used in flood frequency analysis. This is what we have done until now, and you have seen what you see is basically a hydrograph or a daily discharge series. In this series, what you see is daily average flow recorded at the Wabash gauging station in Lafayette. And in this daily discharge series, what you see is the mean value for that day. So for example, on a day, if there was a major flood, this is the peak value. But when you take the average of all these values, you don't get the peak value. Maybe you capture something this. So this series, the daily flow series, usually does not include this. It will include the mean value. So that is something that you want to take into account when you're using this data. So if you really want to capture this peak, you should be using a time series that is not daily but maybe 15 minutes or 30 minutes and so on. But for now in this class we are going to use daily discharge data, and that's what you have used before when you worked with USGS data. So this is the daily discharge series. But in flood frequency analysis, we use a different time series. I'm listing two time series here. One is called annual maximum and the other one is called partial duration. So let me just explain what each means. What I'm showing here is 5 years of data from 2012 to 2017. Okay, and the year that you see here from October to September, this is a water year. Okay, so it's not the calendar year that starts from January and ends in December. So in the United States, the USGS uses a water year that starts on October 1st and ends in September 30th. So in annual maximum series, what we do is we pick the maximum value in that year. So this is the value in 2012, this is the value in 2013, this is the value in 2014, this is the value in 2015, and then this is the value in 2016. Okay, so then you just plot each point against the year and then you get the annual maximum series. So annual maximum series includes the maximum flow for that particular year, and the time scale on the x-axis is 1 year. So for each year you have one value. Now with the annual maximum series, you can see that this year, for example 6017, did not have very high peak values. So when I picked this value here, this value is actually less than this value that you see in year 1415. So when I created my annual maximum series, I missed out some high values in the time series data that I have. So to overcome that, sometimes instead of using one value for each year, what we try to do is we try to define a threshold. So in this case, if I say that my threshold is 40,000 CFS, then what I do is I pick all the values that are above 40,000 CFS, and then I will create my time series. So instead of having one value for each year, some years may have multiple values and some years may not have any value. So for example, instead of 40,000 CFS, if I pick a threshold of 50,000 CFS, then we do not include any values from 1617. So when you define a threshold and pick all the values above that threshold, that series is called partial duration series. Okay, and when you pick one maximum value for each year, then that series is called annual maximum series. This slide just shows the definitions for the annual maximum series and partial duration series. Sometimes the partial duration series is also called peak over threshold series, because as I said, we define a threshold and we pick all the values. As I mentioned earlier, in annual maximum series, the number of data points are equal to the number of years of data. With the peak over threshold series, the number of data points may or may not be equal to the number of data. There is a special case for the partial duration series, which is called annual exceedance series. In annual exceedance series, what we do is we try to define that threshold such that the number of data points is equal to the number of years of data. So when you pick that threshold, instead of calling that series as partial duration series, we can actually call that as annual exceedance series. Now let me go back to this slide. Now I'm focusing on the partial duration series plot here. Now look at this two flow values in year 1415. So if I pick these two, and those of you who have done statistics or probability class, when we pick our data, we want to make sure that all the data points are independent of each other. So sometimes in a partial duration series or annual exceedance series, you may end up picking two flow values that may be related to each other, so they are not independent. So that is a disadvantage of a partial duration series. So that's why I usually use the annual maximum series, and in this class we'll be using annual maximum series for all the flood frequency analysis that we are going to do. Okay, so that's the definition. So what I'm showing you here is annual maximum series for Wabash River in Lafayette. So I have one flow value for each year from 1901 to 2015. And we are interested in finding out what is the return period of 25,000 CFS at this site. So we will be discussing two methods. So the first method is easier and it's sort of graphical. So what I have done here is to find the return period for 75,000 CFS. I draw that line. So another definition of return period is that instead of defining it in exceedance probability terms, we discussed that the average recurrence interval for a certain flow. So the average recurrence interval is the return period. So what we try to do is we try to find out how many times the flow exceeded above 75,000 CFS. So in this case, it exceeded 13 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and maybe here also 13. You can argue that there are 14 values, but again, the thickness of the line is, the red line is thicker here. So I have actually looked at the data, and it's 13 times it was exceeded in the last 114 years. So we have 114 years of data. So what you do then is you try to find the average recurrence interval, the interval that the flow was exceeded. So what I did here is you get the total number of years of data, and then you divide it by the number of intervals. So the number of exceedances were 13. So the interval will be this. So that will be the number of exceedances minus 1. And when you do that, the answer that you get is 9.5 years. And usually we don't say this as 9.5 or 9.4. You will round it up, so approximately 10 years. So the return period for 75,000 CFS at this site is 10 years. And when you have the return period, you can then find the probability associated with it, exceedance probability, so which will be 1 over t. So in this case, there is a 10% chance that the 75,000 CFS flow will be exceeded every year. Okay, so that's one way of finding the exceedance probability or return period corresponding to a certain flow magnitude. Sometimes, instead of asking what is the probability that 75,000 CFS will be exceeded, we are interested in a certain number of years. So if you have designed a bridge or a culvert for, let's say, 25 years or 50 years, so at that time, instead of asking what is the return period for 75,000 CFS, you may be asking what is the probability that 75,000 CFS will be exceeded at least once in the next 25 years. So to do that, again, we can use the theory of probability to find the exceedance probability associated with that. So if we say P or EP is our success, which means the flow gets exceeded, then the probability of failure is 1 minus P. So I have derived the expression that we need to answer this question. So to answer this question, the expression that we have is 1 minus, and inside this parenthesis we have 1 minus 1 over t to the power of n. So n is the number of years that we are interested in, which is 25. So to answer this question, probability that 75,000 CFS exceeded at least once in 25 years. I'm not going to write that. Then you have 1 minus 1 over t. So the t is the return period for the 75,000 CFS, which we found out in the previous slide was 10 years. And then n is 25. So this will be 1 minus 0.1 to the power of 25. So 1 minus 0.9 to the power of 25. And I have actually solved this for you, and the answer is about 93%. So there is a 93% chance that the flow will be exceeded at least once in the next 25 years, and which again makes sense because the return period for this is 10 years. So on average, we would expect that this kind of flow will occur every 10 years on average. So if I'm thinking about 25 years of data, then it is more likely that it will be exceeded at least once. So that's why the probability associated with that is very high, which is 93%. Okay, so this is one way to do this, and as you can see, you need a longer period of data to do this. Another way to do flood frequency analysis when you have data is by using this plotting position, or some people may just call this as ranking of data. So I will just show you a small example here on this slide. So in this case, we are using the Weibull formula to calculate the rank. So Weibull formula says that exceedance probability is equal to rank divided by the number of data points plus 1. So this is the data that is available to us. So as I said, I'm just using a small sample here to show you the method. So in this method, what we do is we sort the data from maximum to minimum because we are interested in high flows. So the maximum value here is 70,000 CFS. So the next one is 57,000 CFS. After that will be 44,000 CFS. After that will be 41,500. After that is 32,000, and then 30,800. So I sorted the data from maximum to minimum, and then we assign the rank. So basically rank highest is 1, 2, 3, 4, 5, 6, and then we calculate the exceedance probability. So this exceedance probability is calculated by using this equation. So in our case, count is equal to 6. The reason we use count plus 1 at the denominator is to make sure that we don't get 100% exceedance probability for any of these values. So for example, if we did not use count plus 1, this value will have an exceedance probability of 100%, which is not likely. So that's the reason why we have count plus 1. So the exceedance probability in this case will be 1 over 6 plus 1, which is 7. So that value comes to around 0.14. Then this will be 2 divided by 7, so 0.29. I have rounded this number, or I have rounded them up to 2 decimals, so that's why if this was 0.14, this should technically be 0.28, but this was not exactly 0.14, so that's why. And then we have 0.43, 0.57, 0.71, and 0.86. Okay, now we are interested in finding the return period corresponding to 40,000 CFS. So once you have the exceedance probability, you find the return period for those. So the return period will be 1 over 0.14 and so on. So you can actually do that and get the return period for this column. Now we don't have exact 40,000 CFS in this column. So what you do is once you get the return period, you sort of interpolate. So you have 41,000 and then you have, so we have 41,000 and then we have 32,000. So when you get the return period for these two rows, you can interpolate between them to get the value corresponding to 40,000 CFS. And usually when you do that, you are not going to get exact year. So it could be 3 point something or 4 point something. So in most cases, you end up with a value that is close to what you have here. So that's how you can handle it, or you can interpolate it. So what I'm going to do is I'm going to show you this in more detail in the assignment that we are going to do corresponding to the return period. So the idea of this slide was to just show you the technique on how to do flood frequency analysis by using this ranking or Weibull formula. And this formula is called plotting position in flood frequency analysis. Okay, so this is how you can do it by ranking method. And then we also looked at how to do it by using this method where you have long period of data and you try to find the average recurrence interval. So with that, I will stop here. In our next video, we will do an assignment on how to use these methods on actual data, and then we will move on to some advanced techniques of doing flood frequency analysis. So with that, I will stop here, and if you have any questions, as always, feel free to email me. Thank you and bye.